Alright, so I want to talk some more about spectral graph theory. Fortunately, this is still right, but not for long. So in previous talks, we've gotten some basic results done. We looked at the Wikipedia article. We looked a little bit at the article by Anderson and Morley, essentially. I'll come back to Fiedler eventually, probably not today, but I would say today we're going to be more into Daniel Spielman's lectures 1, 2, and 3, give or take. So let's see here. Let me get to the new part. All right. I believe after we motivated some of the physical underpinnings of this, we saw some specific examples, and we noticed this plus minus pattern in the eigenvectors for the path graph. We'll come back to that today. And we saw the significance of the zero eigenvalue as it connects to disconnected graphs. The number of disconnected components corresponds to the multiplicity of the geometric multiplicity of the zero eigenvalue. So for example, if there's just one zero eigenvector up to linear dependence, then the graph is connected. I'll give another proof of that today. All right, but we gave a proof before, which was based on playing some games with the complete graph. All right, so let me get to it. Sorry for flipping through here like this. Just trying to. So we went through this proof last time from Anderson and Morley that if we have a graph, weight 1 graph with n vertices and lambda is an eigenvalue of Lg, then lambda is bounded between 0 and n, and lambda equals 0 equals the number of components, in other words, connected components of G. All right. And the proof of that relied on this the complementary graph, and the fact that the union of a graph and its complementary graph give you the complete graph on n vertices. All right. So that brings us to today here. All right. So let me find my cover sheet. So I want to talk more about the structure of a graph Laplacian. So roughly speaking, following parts of lectures 2 and 3 from Daniel Spielman's 2009 course at Yale on spectral graph theory. I found his notes to be very nice to follow. So given a graph, which consists of a vertex set V and an edge set E, we can construct the graph Laplacian L from the weighted adjacency matrix A as L equal D minus A. And the D it's the sum over columns or rows, since A is symmetric, either way you could go. And if we wish to emphasize the connection to G, we could use L sub G for the graph Laplacian of G. All right. So just to recap here, we know that the graph Laplacian has eigenvalues which are non-negative, lambda 1 equal to 0, and we can arrange them like this. Okay. So the nomenclature, the notation we're going to use here is that we'll list them lambda 1 to lambda n, but it could be that lambda 1 equals lambda 2 and so forth. All right. If lambda 2 is not equal to 0, G is connected, and if the weights of the graph are not all 1, if the weights of the graph are all 1, then we know 0 is a lower bound, and which is attained, and n is an upper bound, which may or may not be attained. All right. Now, however, if the weights of the graph are not 1, if they're different things, well then that all bets are off in terms of the spectrum. The spectrum doesn't have to go between 0 and n. Other things can happen. We'll see that today. All right. So again, the proof that we went through last time involved the fact that the union of the graph and its complement was the complete graph. But today I'm going to take a different look at it, using mostly just linear algebra, Alice Spielman's lectures. So before we get to that, though, I just need to take a walk down memory lane, so to speak, and look at some results that we know from linear algebra. One of the things we know is the real spectral theorem for matrices. An n by n real matrix M is orthonormally diagonalizable if and only if it's symmetric, if M transpose is equal to M. And so I'm not going to prove that. That would take a while. to do justice to the proof of that. But I'm more interested in what we can do with it. All right. So this theorem helps us through the calculation. The way this theorem is implemented, rather, is through the calculation of eigenvalues and eigenvectors. In particular, the statement that it's orthonormally diagonalizable, that comes hand in hand with the fact that there's an eigenbasis which is formed by orthonormally selected. You can select them. Eigenvectors are not automatically orthogonal, but you can make them such if you have a symmetric matrix. And so you can find this orthonormal basis, and moreover, the eigenvalues are real. And so you have this data here. You can select eigenvalues real, eigenvectors, and the dot product of them is 1 if they're the same, it's 0 if they're not. And here we're saying vi has eigenvalue lambda I for I equals 1 to n. Now let me just put those things together here and just say a little bit more about that. So my apologies, I don't seem to have any white out on hand, so I'm going to do some scribbling today. You hope you can forgive me. But so we have eigenvectors v1 through vn, and so we have mv1 is lambda 1 v1, and so forth, right? You can take these n vector equations and package them together, just glue them together as one big old matrix equation like this. Here I can pull out the m by the column by column matrix rule. This is how matrix multiplication works. We can pull m out like that. And on the other side, the order matters. You got to pull v out this way, because if you do that, then when we multiply this through, we get lambda 1 times v, which gives me lambda 1 v, because v is, where was that matrix v? Oh, come on. Oh, v is the matrix of eigenvectors. All right, so this, when I multiply this times that, I get that for the first column. This times that, I get that for the second, and so forth. If I wrote the other way, if I wrote lambda v, it wouldn't be right. That's what I had before, so I have it scribbled out. Okay, anyway, the point being, if you have a matrix which is for which you have an eigenbasis, in other words, a diagonalizable matrix, then you can write the matrix times this matrix of eigenvectors is equal to the matrix of eigenvectors times the matrix of eigenvalues, and so that's pretty nice. Now, nicer still, as I'm saying down here, is we can assume that that matrix of eigenvectors has this really nice condition that when you multiply it times its transpose, you get back the identity matrix, which is to say that V is an orthogonal matrix. All right, its transpose is the inverse. Let me move on here. So, as I was just recap again, we have an orthogonal symmetric matrix, we get an orthogonal eigenbasis, at least we can construct it. And so we can write mv equals to v lambda. If we multiply this by v transpose on the right, then what's that get us? That gets us, we get m is equal to v lambda v transpose. So we can rewrite the matrix as the product of the eigenvector matrix, the matrix of this diagonal matrix with eigenvalues down the diagonal, and then the transpose of the eigenmatrix. This is essentially serving in the same role as like the singular value decomposition. That's going to come later. I'm not going to. That's not quite. It's something I said there's not quite right, I think. So we'll have to come back to that in a future lecture. But we're going to use this later, not today. On the other hand, we could multiply the transpose on the other side instead of on the right. We can multiply on the left, and then that gives us v transpose mv equals to lambda. This is explicitly the diagonalization of m to the matrix of eigenvalues. All right. So it's sometimes, make sure I'm in frame here. I forget where I have the camera zoomed to sometimes. All right. So it's sometimes helpful to see. One other thing I should mention, just while I'm going down this memory lane of things we know about diagonalization of symmetric matrices. The other thing to notice is that if m is symmetric, you can actually write it as a weighted linear combination of eigenvalues times these matrices that are formed by the product of a column matrix and a row matrix. These correspond to like projections onto eigenspaces, but I don't need to get into that. Anyway, you can check that that's true by just multiplying that by an arbitrary eigenvector, and you get that they're equal, which goes to show you that this is equal to that since it's matching on its values over a basis. My apologies in advance if the kids get loud here. I foolishly tried to do this video at a time when they're awake. Okay, so what does that have to do with quadratic forms? We're really interested in quadratic forms because the graph Laplacian naturally corresponds to a quadratic form. And I'll get into that in pretty good detail here as we go on. So what is a quadratic form? Well, a quadratic form, without loss of generality, you can assume it's given by a symmetric matrix, let's say M, such that the value for the quadratic form when it inputs x, here x is an n vector, x transpose mx is the formula for that quadratic form. All right. Now there's more pure ways of defining what a quadratic form, but this will suffice for our purposes. A quadratic form is something that has a formula like this. In this context, we'll say that the standard matrix of the quadratic form is M, and we'll write this to denote that if needed. All right, great. So since the matrix for a quadratic form is symmetric, we can introduce eigencoordinates. All right, y equals v transpose x, where v is that matrix of eigenvectors, and with eigenvalues lambda j for vj. And so little calculation right here. Let me scooch it up here a bit so we can see it. So start with q of x, rewrite x is equal to v lambda vy, where y is the eigencoordinate, and then the sock shoes gives us y transpose v transpose. But remember, v transpose mv is the diagonal matrix of eigenvalues. And so when you multiply that back out, you get lambda 1 y1 squared plus lambda 2 y2 squared plus dot 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 plus lambda n yn squared. Well, this is a very nice formula, right? So that's kind of the beauty of this whole orthonormal decomposition, is it gives you a way to take a given quadratic form and write the formula in a way which just makes it so very clear how it works, right? Now I have an example to kind of illustrate how that goes. But just to reiterate, why are we interested in this? Well, we're interested in the graph Laplacian, and the graph Laplacian is a quadratic form, which means that we could, in principle, find these eigencoordinates and write it like this, right? The formula for the graph Laplacian should be expressible in this kind of form as well. So let's look at an example. So I thought I'd start out with something relatively simple, the weighted ring graph. Now I think we looked at, we may have looked at this with like weights 1 in the last, or lecture before last, I can't remember. I should remember, we just looked at the pages here at the start, but you'll forgive me for not remembering. Anyway, so suppose you've got vertices 1, 2, and 3 with weights A, B, and C. This gives us the weighted adjacency matrix ACB, ACB like that, zeros, and then corresponding graph Laplacian over here. A plus C, A plus B, B plus C on the diagonals, and minus A minus C minus A minus B minus C minus B. Quick check, the sum of any row or any column is 0. Very good. Now, that's the graph Laplacian, and it's symmetric. So let's actually take a look at the formula for it. Maybe we can just calculate the formula, you know, and see what the maybe we can see what the eigenvectors look like for this graph here if we just calculate the formula, right? It seems like a reasonable claim. So here we go. Let's get to it. So here we go. Taking the argument for the quadratic form, in this case the graph Laplacian. And so you'll forgive me, I'm going to use the term graph Laplacian interchangeably for the quadratic form as well as the matrix to which that quadratic form corresponds. And that abuse of language is common in this context. But anyway, xyz times this graph Laplacian matrix times xyz like that. So you multiply that thing out, you get this. All right, multiply that out, you get that. Ugh. All right, great. And then if you tilt your head and squint at this, you can start to see some kind of patterns. Like there's an x squared with the a and also with the c. There's a y squared with a and b. There's a z squared with b and c. And let's see here, there's like a minus axy here. There's another minus axy there, so there's like a minus 2axy. And let's see here, there was a, what else was there? Oh, here's an ay squared there too. So anyway, you look at that and you sort things through, and what do you get? Well, collecting things, we get a times that, plus b times that, plus c times that. But you're like, wait a minute, that's a difference of a square, that's a difference of a square, that's a difference of a square. In fact, it's a times x minus y squared, b times y minus z squared, and c times x minus, I'm going to make myself I keep forgetting where the camera goes. I'm just going to stick this pen here so I can remember. C times z minus x squared. Oh no, I just showed you the man behind the curtain. Hope you can forgive me. I'm going to scooch this up a little bit here. Hopefully we can keep track. Alright, so I'm looking at this and I'm thinking, huh, oh, check it out, right? That must mean that the eigenvalues of q, so this is like, remember that like lambda 1 y1 squared plus lambda 2 y2 squared plus lambda 3 y3 squared formula we just saw? So I thought, cool, that means that the eigenvalues of q must be a, b, and c respective, and I could think of these as being eigencoordinates, right? But then I thought, wait a minute, I don't think a or b or c has to be 0 necessarily, and I know that this graph, right, the ring graph, it's certainly connected, so that means that the eigenvalue 0 has to appear once, right, but just once. But where is it in this formula? I don't see it. Do you see it? I don't see it. But I believed in it so much that I had an error here before, and I found a way to put these two together and think, aha, these two go together and that one doesn't go together. And this is wrong, all right? I'm going to scribble it out here in a second. But I talked myself into this in the first place because I wanted 0 to be there so badly as a coefficient. But this is just nonsense. It's not at all what's there. There is, you know, so let's fix that. This is a, you know, what's the word? It's just not true. Because, well, 0 is an eigenvalue. But then well, if 0 is an eigenvalue, how can I have this weighted sum of squares where the weights don't have to be 0? How's this work? Like, what's going on? Like, what happened to the spectral theorem, right? Remember? Right here, we had Q, and when we feed it an entry, think of that as being V for the moment. It's supposed to have a weighted sum of squares where the weights are the eigenvalues. I got this weighted sum of squares here, and yet the weights aren't the eigenvalues apparently because 0 is not in there, right? And we've proved 0 has to be an eigenvalue for a connected graph. Actually, for any graph, 0 is an eigenvalue. So what's going on? Well, so I suffered. This troubled me greatly. Finally, I wrapped my mind around it, and I realized that my defeat, my naivete was trying to just expression match. And I turned to MATLAB's. I mean, just because something's a weighted sum of squares doesn't mean it has to match the eigen weighted sum of squares, all right? And so let me try to unwrap what's going on here. If you do feed this beast to the Symbolic toolbox, MATLAB Symbolic toolbox, which gives you this, you know, graph Laplacian. Well, yep, in fact, yes, 0 is an eigenvalue. But the other two eigenvalues, they're not just A, B, or C, they're these symmetric expressions, which makes sense, right? Because in some sense, there's really no difference between A, B, and C here in 1, 2, 3. There's some kind of like symmetry of exchange of vertices and weights that you could think about. And that is borne out in these formulas down here. As you can see, A plus B plus C, A and B and C are appearing symmetrically. And in here, A squared, B squared, C squared, again, that symmetry between A, B, and C. And we have the product of any two of A, B, and C here. This has to do with those symmetric polynomials. But anyway, there you go. There's stone cold formulas for the eigenvalues of this ring graph. And that is not what we just derived from just multiplying it out, right? Like, so just to, to make it really explicit, on the one hand, for the ring graph, we have this formula just from plain old algebra, this weighted sum of differences. But on the other hand, we have a spectral expansion, lambda 2 y bar squared plus lambda 3 z bar squared, where lambda 2 and lambda 3 are these monstrosities up here. And I'm not even going to try to derive the formulas for y bar and z bar here. They're, I think, pretty non-trivial. I mean, I didn't try to even copy down the eigenvectors for those eigenvalues. They're lengthy symbolic expressions. I can tell you this much, that you define the eigencoordinates by p transpose times the standard coordinate vector. And that's relatively easy to calculate in one sense, because v1 is just 1, 1, 1 divided by the square root of 3 to make it a length 1 vector. And so if you think about this product, you can see that x bar would be 1 over root 3 x plus y plus z. But that's all I'm gonna say about the explicit formulas for the eigencoordinates for even this simple example. Generally, finding formulas for eigencoordinates explicitly is kind of it's a hard calculation. Okay, but it can be done. So that brings me to the homework. So what's going on here, right? So we've seen that we have this, right, and it's equal to that. And so, what's going on? How do we have these two things, where this appears to be giving us eigenvalues with respect to one basis, right, of a, b, and c, whereas the eigenvalues with respect to a different basis are 0, lambda 2, and lambda 3. How can we have that, right? Well, the matrix of a quadratic form does not transform via similarity. Instead, if we look at it, if I do a coordinate change on the formula for a quadratic form, out pops this thing. And let's see here. This is one of those kind of nasty homework problem I'm outlining here. It's based on a confusion, So you gotta be, when you read homework problems like this, you gotta understand the spirit of the question before you waste too many hours. But anyway, I'm getting to it. So here's the formula for the quadratic form. I'm going to insert an identity matrix to identify the coordinate vector with respect to the beta basis. So if I was to change coordinates, the formula for the quadratic form, it has a new matrix right here, which I'm going to define that to be q sub beta. Q sub beta is the basis matrix transpose q times the basis matrix, right? And that's not necessarily a similarity transformation, right? Because a similarity transformation, you'd have to have a matrix and its inverse, right? So unless this basis happens to be orthonormal, they're not going to be similar. Well, okay. So question 1. Now for the homework. Question 1. Find a matrix P such that the matrix with respect to beta 1, and so beta 1 is going to be the matrix for that basis, gives you A 0, 0, 0, B 0, 0, 0, C, and expect then that the coordinates would be x minus y, y minus z, and x minus z from the formula star up there. Now, something I just said there turns out to be factually inaccurate. So this is kind of like a puzzle, like asking you, what's wrong with what I'm saying, okay? So some things are true, some things are not. I may have used a certain word, what I just said, incorrectly. Now, on the other hand, we've got a basis beta 2, which has an eigenbasis, right? And we know that it can, it's orthonormal actually, so this is the inverse for what it's worth, and that's actually a diagonalization, and it works out to this, all right? And then question 3, say, okay, so from q beta 1 we saw eigenvalues a, b, c, right? diagonal matrix. That's the eigenvalues in the diagonal. And from Q beta 2, we see eigenvalues 0, lambda 1, lambda 3. But what about Sylvester's theorem? See, because Sylvester's theorem says that if we think about A being Q and B being P transpose AP for B equal to that, where this base is beta 1, then supposedly A and B are supposed to have the same number of 0 eigenvalues and the same number of positive and negative eigenvalues. And yet, golly, George, that's not the case here, because I'm assuming A, B, and C are positive, all right? And there's no 0 eigenvalue up here, but there is a 0 eigenvalue down here. How's that go? What's going on there? So that's your homework assignment. Try to explain that. All right. If you, well, anyway, I'll just leave it at that. So I'm gonna leave that as kind of an open question for the moment. Maybe I'll come back and give you the answer at the end of the video if we have time. All right, so moving along here. So I want to just go basically generalize. So we went through a specific argument for the, let's see here, the ring graph, right? Where we just saw that there's a super nifty formula that makes a lot of sense. A times x minus y, b times y minus c, z times c times z minus x, right? And that makes a lot of sense because when we look at the graph, like x is going with that, y is going with that, z is going with that, so it's like x minus y times a squared, you know, y minus z times with a b out front, and over here is z minus x times c. So you can see where that formula is coming from in terms of the original graph. It's not really surprising. And in fact, that is actually how Spielmann defines the graph Laplacian at some point. But I want to derive it, so I'm going to do that. So, because we've defined the graph Laplacian as D minus A, where A is the weighted adjacency matrix, and we have D as the diagonal of the column sums, or you could use row sums. And we've noticed that 1, 1, 1, 1, 1 is an eigenvector of L with eigenvalue lambda 1 equals 0, and that is not just true for our examples, it's generally true. Here's the calculation, right? So we take 1, 1, 1 times that diagonal matrix times A times 1, 1, 1. When I multiply the diagonal matrix times that, I get this column vector, and when I take A times that matrix, I get this column vector. However, this and that are the same because A is symmetric, so the column is the row in terms of components, right? This is actually the same sum. So there you go, 1, 1, 1, 1, 1, 1, 1, 1. N-fold times is an eigenvector with eigenvalue 0. It may or may not be the only one, depending on what else is going on, right? And so let me just also make sure we have some terminology down here. We can write the matrix A as a sum over edges, weights times, so this EIJ is a matrix with mostly zeros, but just a 1 in the I equals K and J equals L spots, all right? Rather, K equals I and L equals J spot. So the KL component is only non-zero if K matches I and L matches J. And I'm just going to assume that these weights are ordered such that I is less than J, because I don't want to double count. That's one criticism I have, is like Spielmann's, you know, he doesn't care that much about that kind of detail, and so some of his sums you might, depending on your background, get confused about what they mean, but that's okay. But I'm just going to be boring and assume that the edges have to go like 1, 2. And I think Spielmann actually generally does that, except where he doesn't. So to make, this makes A symmetric, all right? And it follows that the graph Laplacian is likewise symmetric, which is great because then the real spectral theorem applies, right? Okay, so moving along here. If M is symmetric and it's like the graph Laplacian, if M times the all one vector is 0, then you can rewrite M as a sum over I less than J minus Mij Lij, where this Lij is this matrix which just has 4 non-zero entries. It's got a 1 in the II spot, another 1 in the JJ spot, a -1 in the ijth component, and a -1 in the jith component. So it's a matrix of all zeros, n by n matrix, all zeros, except for these 4 non-zero components. And it corresponds to an edge going from I to j, if we go back to the graph theory. But let's just talk about the matrix here for a bit. So, just going to work through it. So M1 provides that the ith row of M dotted with the 1, 1, 1 vector is 0, which means that the sum over j equals 1 to n of mij is 0. So I can solve that for mii, and I get mii is equal to minus the sum over I not equal to j of minus mij. And I can do that for each I. Great. Consider then, you can take any matrix and you can write it as a sum of the matrix units, right? This is just taking a matrix and ripping it apart into its fundamental building blocks. And if you think about components to a matrix, there are really 3 cases. The diagonal, let's see, I less than j, that would be like 1, 2, or 2, 3, or 5, 6, or let's see, I'm trying to think, is that above or below the diagonal? That would be above. These are the above the diagonal sort of things, and these would be like lower, below, so upper triangular, lower triangular, right? So any matrix is a sum of a diagonal, a upper triangular, and a lower triangular matrix, just like that. But I can also play a trick here because M is assumed to be symmetric, so I know that Mij is equal to Mji, and so I can switch the sum over I and j to the sum over I greater than j to the sum over j greater than I, and switch the I and the j here, right here, to get the Eji, but then switch that Mji back to Mij because of the symmetry, and that gives me down to here, and I just have some Mi less than j of that. So that's pretty sneaky. And then I can rewrite this Mii as the sum over I not equal to j of minus Mij, as we just talked about. And then, what do? Something similarly sneaky. And then I can look at that as, well, that's really the sum of I not equal to j breaks into 2 cases, right? I less than j and I greater than j. And I still got that term over there. Great. And then, what do? Well, I flip the sum again, I believe. I switch I to j and j to I. Gets me down to here, like that, right? And then I use symmetry to pull out Mij again. And I combine the sums at this point, and I've just got that. But that is, lo and behold, exactly the L sub I comma j matrix. And so what we've just shown is that any symmetric matrix that has the all one vector in its null space can be written as this linear combination of these particular matrices which have just these 4 non-zero components, and they correspond to an edge going from I to j as it happens. Now that's okay. You're like, okay, well, that's lovely. Who cares? Well, fair enough. I think in isolation that result's just kind of a snooze. Maybe this all is. I don't know. Go get some coffee. Hit pause. Come back. Do some jumping jacks. Whatever it takes. Eat a candy bar. Whatever it takes. I don't know. Let's see here. So for Lij, just as we defined, where this is the usual matrix unit, we can prove that for the if we sandwich this, let's call this the edge matrix, the Ij edge matrix. If I sandwich it's not that. It's it's really the graph Laplacian for just an edge. I don't know. Spielman has a better discussion of this than I'm giving at the moment. But anyway, multiply x transpose times that, I just get the difference of the ith and the jth coordinate of x squared. That's kind of snazzy because, and here's the proof of it, which is just the usual standard basis kind of stuff. Like I'm saying that you can take any matrix unit and write it as a product of the standard basis, just like that. And if you do that, then you can expand this guy in terms of products of the standard basis vectors, and then when you multiply x transpose and x on that, you get like, gives you like an x ei dot x, this gives you like an x dot ej, ej dot x, x dot ei, ej dot x, x dot ej, is dot products all around. And I'm about to say they cancel, but that's not accurate. They don't cancel, but what they do, because of the symmetry of the dot product, is two of them combine. So you get like 2 xi xj from this guy and that guy. And the other ones just give you xi squared and xj squared. So you get xi squared plus xj squared minus 2 xi xj, which of course you'll recognize as xi minus xj squared, which is pretty fantastic, because when you combine it with the theorem that we just had on the previous page, what do you get? Well, you get, if you have the adjacency matrix with weights wij and the corresponding graph Laplacian L equals d minus a, which is a symmetric matrix, which takes 1, 1, 1, 1, 1, 1, 1, 1, however, n-fold times as a null vector, it's a zero eigenvector. So that means we can write L as this kind of sum over those L I comma j matrices, right? And then if I sandwich L between a vector, transposing it in to get the formula for the graph Laplacian, when I put that in here, well, that just gives me back xi minus xj squared times the weight. And so this shows that what we did for the ring graph with the ABC ring graph, it generalizes. In fact, anytime you have a graph Laplacian where we construct as L equals d minus a, you can rewrite it as a sum over weights times the squares of difference of connected vertices. And it's just that simple. It's a beautiful formula. Really quite beautiful. And so once you have that formula, you can prove basic results, right? So we'll reprove some of the things we did in previous lectures using quite different arguments. Because now we have a stone-cold formula for the graph Laplacian, and it just makes things easy. For example, the eigenvalues of the graph Laplacian are non-negative. Well, if you suppose you've got an eigenvalue, right, lambda, and you plug that thing into the formula, like that, right? Well, what do you get out? You get q of v is this times that minus that squared. But on the other hand, it's lambda times v dot v, right? And v dot v, well, that's the length of v squared. So you've got this positive weighted sum of squares is equal to lambda times a positive thing. It forces, I mean, the only thing that can happen is somehow these differences are all zero, right? Which could happen either if like a bunch of zeros are in the vector and other ones that are adjacent are matching, like it happens with the 1, 1, 1, 1, 1, 1, 1 vector, all these differences are zero, so it allows lambda to be zero. If you go back to previous talks and you think about other zero eigenvectors, you'll see that they make all of these differences to be zero. But anyway, there you go. That forces this to be non-negative because it's built from a positive sum of squares. All right, great. And also, we get a pretty quick proof of connectedness. Let me go through that. So if we have a graph with eigenvalues, 0 equals lambda 1 all the way out to lambda n for L. And again, we've already proved that 0 is an eigenvalue, right, for the 1, 1, 1, 1 vector. Then lambda 2 is positive if and only if G is connected. All right, so here's the proof. And I just follow Spielman, okay? But he starts out by saying, well, I mean, he doesn't say this, but I say this. By the way, lambda 2 not being 0, lambda 2 being positive is the same as lambda 2 being not 0, right? So, all right. And then he says, okay, so suppose G is disconnected. All right. And so I would just point out what he's doing here is using this little bit of logic, right? P, if and only if Q, it requires the implication P implies Q to be true and also Q implies P to be true, right? This biconditional. But you can trade this one for not P implies not Q. And that's what he's doing right now. He's just he's assuming, suppose instead of think of P being the condition G is connected, he's saying suppose suppose G is disconnected. That's like the not P, right? Now he's going to try to show not Q. What's not Q? Not Q is that lambda 2 is not greater than 0, right? Which would be what? Which would force lambda 2 to be equal to 0. That's what he's going to argue, right? So let's see how he does it. So suppose G is disconnected. That means it can be written as the union of two disconnected disjoint graphs. And after relabeling as needed, we can make the graph Laplacian look like this, because again, there's no edges connecting the vertices in G1 and G2 respective. But on the other hand, since these are graph Laplacians, thinking of the disconnected components separately as their own graphs, we know that there's a 1 vector as big as G1 and a 1 vector as big as G2, which are null vectors for those graph Laplacians, subgraph Laplacians if you like. And so this and that are eigenvectors of LG, in fact, because when we multiply that times this, we get 0 from L1, because that's 0, and when we multiply this times that, we get 0 from the block multiplication, but we also get 0 because G2, 1, G2 equal to 0. So in short, this and that are eigenvectors with eigenvalue 0, and so that means that lambda 2 is also 0, right? So, because these are not linearly dependent. All right, so the other direction, so we just did Q implies P, right? By doing the contrapositive, I think, and now we want to do P implies Q. So conversely, suppose G is connected, all right, and suppose we have x not equal to 0 such that it's a zero eigenvector. We'd like to force x to be the 1, 1, 1, 1 vector, right, up to a multiple. So here's how that goes. So x transpose Lx equal to 0 by our wonderful formula implies it's the weighted sum of difference, positive weighted sum of the squared differences of the components of x. But that means that if, how can you have a sum of differences squared be 0 where these are all positive for every ij in the edge set? Well, it must be that these are 0, right? Which forces xi to equal xj for all I and j in the edge set. All right? So, suppose you have any choice of I1 and I2 in the vertex set. Then because G is connected, there exists a sequence of edges connecting these vertices, which is in the edge set, right? Going from I1 to I2. But that then means that x1 is equal to xi1 is equal to xj1, which is equal to xj2, and so forth and so on is equal to xjs, which is equal to xi2, which shows you that xi1 is equal to xi2. But I1 and I2 are arbitrary components in this 0 eigenvector, and we've just shown that all the components then, because an arbitrary pair has to be equal, So all the components of x match, which implies that lambda 2 is positive. What? Oh, yeah. So yes. All right. So what that shows is that there's just one eigenvector up to linear dependence because it's just the constant vector, which is eigenvalue 0. That's what this calculation shows. Therefore, the next one, corresponding to eigenvalue lambda 2, must be positive because it. If you did assume that lambda 2 is also equal to 0, you'd get a contradiction. You'd forced it to be linearly dependent on this constant vector. And remember, our context here is working with the graph Laplacian, which we know has an eigenbasis, right? So if we enumerate the eigenvectors 1 through n, then each eigenvector corresponding to each eigenvalue has to be linearly independent, otherwise our whole system of nomenclature falls down. All right, so I think I'm going to take a break and start again here. I still haven't answered the mystery of the homework question. Maybe I'll come back to it in the next video. Thanks, guys.